Hello, my name is Yelisei. I'm a first-year graduate student in the Quantitative Concentration of the Psychological Sciences program. I'm also a graduate assistant in the Center for Assessment and Research Studies, or CARS for short, where I help evaluate student learning in JMU's general education programs. For the graduate showcase, I will be presenting on Understanding Radar Effects, an application of Rasch measurement in arts and humanities, which is a research project that evolved from my assistantship work. Before we jump right into the research, let's look at a roadmap of what will be covered in this presentation. We will begin by developing a conceptual understanding of what radar effects are and why they are important. Then I will introduce the context of the present study, which will illustrate how we can employ particular measurement models to understand these effects in the context of an arts and humanities general education assessment at JMU. This is followed by analyzing a measurement model to examine radar severity, consistency, and use of a rubric in the arts and humanities assessment. We're going to start building our conceptual understanding of radar effects by talking about the Olympics. Every 4 years, this high-stakes competition among nations brings in substantial revenue and countless viewers from across the world. Athletes dedicate their lives to be declared the best at a given sport, and many of these competitions require expert judges to determine who performed the best. One such popular event is figure skating. Yoona Kim from South Korea was predicted to win the gold in ladies event at the 2014 Sochi Olympics, but Russian skater Adelina Sotnikova ended up winning the gold, even after making a big mistake. This led many people to ask about whether the judges had a nationalistic bias. In other words, these raters were judging skaters from their native country more leniently or favorably, while other skaters are judged more severely or harshly. Now, this doesn't seem fair, but we can't score figure skating without using expert judges. Moreover, there are a series of other effects that judges can exhibit without being explicitly biased. For illustrative purposes, let's pretend you are competing in a baking contest. Your task is to make a cake. However, you happen to get Gordon Ramsay as a judge, who is notoriously difficult to impress, while I, your competitor, am judged by my grandmother, and I happen to be her favorite child. Should I win if I receive a higher score? In this example, it is clear that I should not, because the scores are influenced by who happens to judge our cake. The scores we would get would not be representative of our baking ability alone, but a factor of which rater we had. Ultimately, we don't want our scores to depend on which rater a person gets, so we need to know about these rater tendencies. If we understand rater tendencies, then we'll be more capable of accounting for these issues when assigning scores. Here at JMU, we also find ourselves in situations where rater effects can influence student scores. Take the Arts and Humanities General Education cluster, for example. Students meet this graduation requirement by taking one class in each of three areas: human questions and context, performing arts, and literature. During assessment day, students watch a 25-minute long foreign film and then respond to 5 open-ended questions. These prompts include: what does this work communicate to you? Using examples from the film, describe how specific techniques and tactics are used to convey meaning. What questions would you have about this work for its creators? Regarding this work, what questions would someone doing scholarship in arts and humanities be interested in exploring? And how does your culture affect the way you understand this work? Students' answers are graded by a rubric with scores ranging from 0 to 4. Each performance level is defined by the rubric. These 5 essay responses are judged by at least 2 of 5 expert judges, which are faculty members of the arts and humanities disciplines. These judges go through rated training where they are calibrated on how to interpret and apply the rubric to student responses. This involves going over a few clear examples of high scoring and low scoring responses from previous years as a group. Then, individually, judges rate 5 new student responses and convene to discuss rater discrepancies, after which the remaining student essays are split up such that each student response has 2 raters and the raters are overlapping. The sample consists of 50 first-year students that have not taken any required courses and 41 sophomore students that have completed the cluster requirement. Now we can look at our Rasch measurement model for this data. The first thing we might want to know is the severity of our judges. To do this, we can look at something called a variable map. When interpreting this map, we can see in the first column something referred to as our measure. This is a logit. and we can generally think of the 0 as something like an average. Our students are in the next column. Higher values indicate students with greater estimated ability than students with lower values. Next, we can see our column for our 5 raters. In this case, raters with higher values are more severe than raters with lower values. As we can see from this table, 2 judges are close to our average. Rater 1 is a little more severe than others, whereas raters 2 and 3 are a little less severe. Although we see these slight differences, our tests indicate that the raters are not different enough from each other to be a cause for concern. Moreover, all of their responses adequately fit our measurement model, so no judges are behaving in ways that are unexpected if the data is behaving properly. As can be seen by infit and outfit values that give a sense of rater consistency. If a judge tends to give scores that are too idiosyncratic or inconsistent, then they will have high infit and outfit values, meaning that their scores are causing too much noise and degrading the Rasch measurement model. If a judge tends to give scores that are too predictable, as in too consistent, then they will have low infit and outfit. Infit and outfit range from 0 and higher. A general rule of thumb is that good values are between 0.7 and 1.3. Basically, values within this range mean that the scores the judges provide fit the data well. Judges that are outside these ranges can be flagged for rater training. This can also be illustrated by examining differences between the average we observe for each student and what values are obtained after being adjusted according to the model, known as a fair average. A quick overview of these responses shows us that both the observed and expected averages are very similar, as seen by a 92% correlation between assigned scores and scores adjusted for rater effect. This implies that there will be little differences between the scores we see that are assigned to students and those that are adjusted. Lastly, we might also be interested to see how the judges are applying the rubric. To do this, we can look at these probability curves. These curves can be a bit difficult to interpret, so let's begin by looking at the x-axis, which has differences in student ability. On the y-axis, we have the probability of a particular response. Each curve represents each category 0 to 4 on our rubric scale. Let's look at an example to see how we can interpret this figure. For instance, let's say we have a student with an ability measure of 2. What rating would these judges give him? We can follow the horizontal axis and see that an ability measure of 2 is most likely to get a rating of 3. Here we want to see that our thresholds make sense. The thresholds can be thought of as intersection points because it illustrates the ability level at which there is an equal probability of being in adjacent categories. For example, negative 3.11 is the ability at which a student has an equal chance of being in a 0 or 1. It is important that these thresholds are ordered correctly from lowest ability categories to highest, as we see in this case. Additionally, when interpreting these, we can think of the picture as a series of mountains. Each of the mountains should peak and be distinct from other mountains, which is the case with our data. In other words, it looks as though our rubric measuring scale is functioning as expected. However, if one category never had a distinct peak, then we might want to flag it as if to see if judges understand what that rubric criteria is asking, how it should look like in student work, and if the rubric itself needs to be reworked. In conclusion, we have reassuring takeaways for the arts and humanities assessment. While raters do vary in severity and leniency, our evidence indicates that they are more similar than different. Each rater had a tendency to provide scores that were expected according to our measurement model. Thus, our observed scores generally aligned with scores adjusted by the model. And in general, raters seem to be using the rubric appropriately. Thank you for listening to my presentation. If you have any questions, post them in the Graduate Showcase chat blog, and I will be responding to them between April 27th through May 1st. Feel free to contact me at my Duke's email if you have further interest in Rasch measurement modeling.